So now that we covered the entire reasoning underlying statistical testing, now that we know what the p-value represents and how it ties together with statistical significance, it's time to delve into the code. And in fact, there are a couple of reasons why it is beneficial to do this at this point, and which make this lesson quite important. The first reason being that we will generate all of the graphs that we saw in the slides ourselves in this code, and thereby get a better understanding what they actually represent. The second reason, and arguably the most important reason, is that by going through the code, we are allowed to have another pass of going through the entire reasoning, but now alongside implementing it in Python code. Instead of immediately using the built-in Python function and thereby computing the p-value in just one line of code, we will compute the p-value manually, and thereby get a feeling of how it is actually built up. And the third reason is that because we have so much control over our data, because we generate it ourselves, at the end of the lesson, we will play around with the parameters to showcase scenarios that really exhibit the power and strength of the p-value, but also crucially, where the p-value fails. So let's get into the code. The first step, as always, is to generate our populations. So we define a population size of 100,000 data points, and population 1 will be a normal distribution with a mean of 1 and a standard deviation of 0.5. Now population 2 will also be a normal distribution with the same standard deviation, but with a mean of 1.3. And therefore, we now have generated two populations for which we know that the mean will be significantly different. In this case, a difference of 30%. The second step is then to generate samples from these populations. One sample for each population. Now the sample size, which is the number of data points for each sample, will be 15. Therefore, the same as always, we choose 15 data points from population 1 at random, and this generates our sample 1. Now for sample 2, again, we choose 15 data points from population 2 at random. So at this point, we now have two populations and two corresponding samples. And of course, the challenge or the question that we're trying to answer is, can we derive the difference in means of our populations by only looking at our sample data? And that is, of course, what statistical testing is all about. Now, the first step, of course, is to compute some sample statistics. We compute the mean of sample 1 and the mean of sample 2. Now, in reality, these are the only two means that we have, because the population distributions are, of course, unavailable to us. We also compute the variance of sample 1 and the variance of sample 2. And now the important metric is the difference between sample means. So we take the mean of sample 1 and we subtract the mean of sample 2. Now this will give us a number, the observed difference. And then again, the challenge is to, by judging only on this number, can we deduce or conclude that there will be a significant difference in mean of the underlying populations from which these samples are drawn. And before we tackle that question, we can of course already print to see what we've gotten thus far. We print our sample mean 1 and our sample mean 2. And then of course we also print out the observed difference that we have. So if we scroll down and look at the first output of this cell, then we see indeed that in this case the mean of sample 1 is 0.909 and the mean of sample 2 is 1.28. And then the resulting difference in means between these two samples is minus 0.371. Now this is in line with the difference in the population means, which we set to be 0.3. So then the question of course is this result from our sample statistics significant or not? And that is what we will do. So scrolling back to where we left off, we get to this part of the code. Now in this part of the code, what we need to do is we first need to generate this distribution that represents the null hypothesis. Remember, the null hypothesis is the assumption that the underlying populations are identical in the statistic that we're looking at. In this case, the mean. So the null hypothesis is that the means of the populations are identical. Now, we know, of course, that this is not the case in our example because we deliberately set them to be different, but in reality, you don't have this information. So how do we then generate this distribution of differences of sample means under the null hypothesis? Well, we will follow the insights gathered by mathematicians. In fact, they found that the distribution, specifically for the differences in means, follows approximately a normal distribution. And this approximate normal distribution is centered around the value of 0. And this reflects the null hypothesis, because if our underlying populations have a mean that is identical, then taking samples from these populations and subtracting the means from these samples, then on average, we expect this difference in means to be 0. Now, the variance of this distribution will be equal to the variance of our sample 1 divided by the number of sample data points of sample 1 plus the variance of sample 2 divided by the number of data points of sample 2. So with this information, we can generate this distribution of sample means. So we define the mean of the distribution up front to be 0. We define the variance of this distribution according to the formula handed to us by our friendly mathematicians. And then we define a new Python array in the same way as we did before. Just numpy.random.normal to make a normal distribution. The mean or location of this distribution will be 0, our mean difference. And the standard deviation will be the square root of the variance. But the variance we defined here already. So we just plug it in here. And the size of this distribution doesn't really matter. Just make it very large. In this case, we take it the same as the population size. And this will give us a normal distribution that represents the difference in sample means under the null hypothesis. Now, as I said before, this is just an approximation of the real distribution, because in reality, this distribution should be a student's t-distribution, which is very similar in shape to the normal distribution, but it has much larger tails. But because we're more familiar with generating normal distributions, we opt here to generate this distribution as being a normal distribution. Now, this approximation will reflect itself in the eventual p-value that we will compute and compare it with the built-in p-value from Python. Now, we will also see that by changing and tuning the parameters, most notably increasing the sample size of our samples, that this approximation becomes better and better. And our two p-values that we compute, they will converge. So just keep this in mind for later. So at this point, we have our two samples, the means of our two samples, and thus the observed difference in sample means, and now also the distribution against which we can compare our observed difference and see how extreme it is compared to the other values in this distribution. And so the next step is to actually determine the statistical significance that we want to use in this example. Now, in most cases, this cutoff value is a p-value of 0.05, and that's also what we will use in this scenario. So we define our p-value cutoff to be 0.05. So now that we have determined our statistical significance level, namely a p-value cutoff of 0.05, we want to find the corresponding values in the underlying distribution of sample differences, because we want to be able to determine whether our observed sample difference of means falls within the 5% most extreme values of this distribution. Now, because this is a normal distribution and thus a symmetrical distribution, these 5% most extreme values will be cut in half and be found at the two tail ends in our histogram. 2.5% on the left side of our histogram and 2.5% on the right side of our histogram. And thus we need to find the values in our difference distribution that indicate this boundary between the 2.5% most extreme values at this side of the histogram. And this of course calls for the usage of percentiles. Because remember, the 5th percentile, for instance, gives you the specific value of your distribution for which 5% of values are lower than that. But in this case, we don't need the 5th percentile, we need the 2.5% lowest values of our distribution and the 2.5% largest values. So we actually need two numbers. The lower value will be the 2.5th percentile, so the percentile corresponding to 2.5% of our population of sample differences. And this number right here should be just 2.5. We have our p-value cutoff, which is 0.05. We divide it by 2 and we multiply by 100 to get a percentage. Now for the upper bound, we need the 2.5% largest value. Now this corresponds to 100% minus 2.5%. So the percentile corresponding to 97.5%. And this is exactly what this number is. So we have our p-value cutoff, we divide it by 2, so we get 0.0025, and then we subtract this from 1. This gives us 0.975, and we multiply by 100. And at this point, we now have two values from our underlying distribution of sample differences that indicate the 2.5% most extreme values, both at the lower end and at the upper end. The next step is to create a cumulative distribution function. Now, this can be very easily done by making two arrays. The first array will just be the sorted array of our population of sample differences. And then the second array will be this array of linearly spaced numbers between 0 and 1, and which will be the same size as the underlying population. In this case, 100,000 points. And these two arrays will together represent our cumulative distribution function. Because if you compare them element-wise, then each element or each value from our underlying distribution of sample differences will be paired with a percentage of data that is lower than this value compared to the entire distribution. And at this point, we have all of the ingredients that we require to actually compute the p-value. Now, these values are defined in order to make some nice visualizations on the plots, and the rest of this cell is basically all plotting. Now, if we scroll down to the plots and we see what we eventually want to get, on the first graph, we represent our populations by their histograms. And here, of course, we very clearly see that there is a difference in means between these two populations. Then on the right-hand side, we plot the histograms of our specific samples. And of course, the corresponding sample means are the vertical lines here. Then on this graph, we represent the histogram of the distribution of sample means. It's this normal distribution that approximates the student t-distribution. And on it, we have the vertical red line indicating the specific observed difference in sample means. Basically, it's the difference between these two lines here. And then we can see where it exactly falls within this larger scope of this distribution. Now, on this graph, we also see the bounding values of this distribution that indicate the 5% most extreme values. We have an upper bound indicating the upper 2.5% most extreme values, and we have a lower bound indicating the lower 2.5% of extreme values. And then we can use these two boundaries to visually inspect whether our observed difference in sample means, the red line here, which represents the difference between the sample means, falls within the 5% most extreme values, so it falls within the red regions, or not, if it falls in this blue region. Now, the same information is encapsulated in this graph to the right, which is our cumulative distribution function. Now, the same information is on this graph, but now only with respect to the percentiles on the y-axis. Now, what I will not discuss in detail here is how to make these shaded areas on these graphs, and specifically on this cumulative distribution function. This would take us too long, and that is why I of course refer you to the corresponding video where I do go into detail on the Code for Data Science YouTube channel that belongs to this course. So let's briefly scroll up and see how we can plot the elements that we do have. So of course, we define our figure and our axis. First, we plot our histograms, which is very straightforward because we did it a lot of times by now. Then we plot our sample histograms with, of course, the sample means as vertical lines. Then on the bottom left panel, we plot the histogram of our distribution of sample means, this approximate normal distribution. And then the rest of this code will take care of these shaded regions, so we will not discuss it here. Now, of course, in the last panel, we plot our CDF, our cumulative distribution function. And also here, the rest of this code will take care of the shaded regions on this specific plot. And then we just do plot.show to give our final result. And we can run this cell and see indeed that we get these plots. And in this specific case, our sample difference falls within the blue region. Now, to conclude this exercise, there is of course one more thing that we need to do. Namely, we need to compute the p-value for our observed difference in sample statistics. Let's say in this case, for instance, we have an observed difference in means between our samples of minus 0.173. Now we want to compute the p-value for this specific sample to see whether it is statistically significant or not. Now remember, the p-value for a specific observed sample statistic is the percentage of data in our underlying distribution of sample statistics that is equal or more extreme than our observed value. In this case, our observed value is this red line right here, this minus 0.173, and we want to compute the percentage of data in this distribution that is more extreme. Now these percentages are more clear if we look at our cumulative distribution function. We see that our specific observed value, this 0.173, lies at the roughly 20%. So this means that 20% of data is lower than our observed value and thus more extreme on the left-hand side of our histogram. But because we have a symmetric distribution, this also means that we have 20% of data that would be larger than our observed value. And thus 20% plus 20% is 40%. So this would give us a p-value of roughly 40%, because 40% of data would be more extreme than our observed sample. And if we scroll down a little bit, then we indeed see that for our manual p-value and our built-in p-value, we get a p-value of roughly 40%. So let's now see how we can actually compute these values. And this can be done quite easily. The first step is to find the percentage of data of the underlying distribution that is either lower or higher than our observed value. Now this lower or higher depends on which side of the histogram our observed value falls. If it falls on the left-hand side of our histogram, which was the case in our example, then we want to find the percentage of data that is lower than our observed value. If our observed value falls at the right side of the histogram, then we want to find the percentage of data that is larger than our observed value. And that is exactly what is done in this line of code. This stats.norm.cdf function first creates a theoretical normal distribution based on a mean, which will be our distribution of differences mean, and a scale or standard deviation, which will be the corresponding variance and then the square root of this variance. Then it will make a cumulative distribution function of this corresponding normal distribution, and then it will look at the specific value and say what percentage of values is lower than this specific value. And thus, this line then indeed gives us the percentage of values of the underlying distribution that is lower than our observed value. Now on the right side of our histogram, this function would give us a large number, because if we are on the right hand side, there will be a lot of data that is lower than our observed value. And therefore we subtract this number from 1. And then we take the minimum of these two values to pick out the right one, depending on which side of our histogram our observed value falls. And this gives us the percentage of values of our underlying distribution that are more extreme than our observed value. Of course, only on one side of the histogram. Now, because our distribution is symmetrical, and thus the histogram is symmetrical, we can simply multiply this number by 2 to get the final p-value, namely the percentage of data points of our underlying distribution of sample differences that is more extreme than our specific observed sample difference. Now, all of the work that we did and all of the calculations that we performed to get our eventual p-value can also be obtained in just one line of code using this built-in Python function. So our p-value will be equal to stats.tTest independent, and in later lessons we will see that the independent t-test is indeed the test that needs to be applied in this scenario. We give it sample 1, we give it sample 2, we add .p-value, and we already have our p-value. And now we only need to judge whether it's larger or lower than our statistical significance level, in this case 0.05. Now, in real-life scenarios, using this one line of code is indeed the way forward. Just use the Python built-in functions to do your statistical testing, and then look at the resulting p-value to make your conclusions. However, because this is so easy to do, most professionals that use it don't really understand what the p-value actually represents. But now, by computing the p-value manually just once, you really understand what is going on under the hood. Another benefit in really understanding how the p-value is built up is to be able to better judge in which scenarios it will give a good result and in which scenarios it will fail. And that is something that we will do in the next lesson. By fine-tuning the parameters in our code cell, we can simulate different scenarios and see how this influences our p-value and our eventual conclusion.